So all these sessions will be recorded and will be put on the Ego4D YouTube channel. The first session focuses on viewpoint selection and generation. Again, one of the big advantages of Ego4D is EgoExo, is the presence of multiple viewpoints and multiple exo viewpoints, which have triggered a new line stream of research into correspondence between these two views, generation, selection of which view to learn from for the different types of activities, and also how to utilize the multiple views to achieve better performance. And in the first session, we will have 4 talks. We will be starting by a talk from NUS for a work that is to be presented at NeurIPS next week. And then we will go into a work by UNC Chapel, which was presented at ECCV, a work at UT Austin on ArXiv, and finally back to a work by that was presented at ECCV. So Jiawei, Feng, Sagnik, and Camillo will be presenting. They have been promoted to panelists, so hopefully you'll be able to share your screens. It is a 10-minute presentation followed by maximum 5 minutes for questions. Everybody can ask questions, not those only on the panel. So you can type your question or just raise your hand and we can give you the microphone to speak. For those speaking in the second session, I will just add you as panelists during the break. Great. So thanks again for everybody who's joining today after the second session, and for those newly joining. This is a new adventure we're trying out. Please send feedback to see if this was a good idea to share the latest and greatest of works that have utilized Ego4D and EgoExo4D by members of the consortium. And I will stop sharing my screen, and Jiawei is mostly for you to share your screen.
Thank you. Can you see my screen?
We can see your screen, we can hear you, and we're ready.
Okay, hello everyone. I'm Jiawei from National University of Singapore, working with Professor Maxwell. I'm very happy to introduce our recent work on the exocentric-to-egocentric video generation in NeurIPS this year. So we base our work on the Ego4D dataset. The definition of this work is that given the 4 exocentric videos, we aim to generate its corresponding egocentric videos. So specifically, given these 4 exocentric videos that are configured 360 degrees around the direct skilled human activity, such as the human playing basketball in the court or doing CPR in the indoor rooms and also cooking in the kitchen, we aim to generate the corresponding egocentric videos with the same activity and the environment as the exocentric ones. Like in this column is our generated egocentric videos in comparison to this ground truth videos. Why this task is important? Because the exo-to-ego is very important for both humans and AI robots. When people observe and learn skills from the exo perspective, we can easily envision ourselves doing the skills from our first-person views. But it's still quite challenging to achieve such exo-to-ego generation, especially for Ego4D. The first reason is because due to the significant difference and the variations between exo and ego viewpoints, this can result in the large occlusions and small overlaps between exo and ego views. And secondly, it's due to the high complexity of the dynamic motions and also the daily life environments, such as kitchens. So for the SOTAs in this field, it's exo-to-ego and also 40D later Cheng will introduce as one of the pioneering works in this field. The mainly targets the image level exo-to-ego translation. So for the exo-to-ego, they leverage the hand pose as guidance to generate the ego image. So they first generate the ego hand pose given this exo hand pose, and then utilize it to generate the final ego image. But this would require the ESO camera to be placed close to the activity, like in this one, so that it can capture the EXO hand pose in the first place. And also, they target at the image level translation. Well, different from their method, we target at a more complex scenario of the Ego4D, where the EXO cameras could be quite far from the subject, where it's difficult to directly capture the hand pose from the EXO camera. And secondly, we aim at the first video level EXO-to-ego generation. So this is a pipeline of our framework. So essentially, our model is a conditional egocentric video diffusion model. And I use this point cloud to just visualize this kitchen. And also these yellow cameras represent the locations of this EXO camera, and also they are captured EXO videos. And this red camera is the Ego camera, which we aim to generate in this final stage. So recall the major challenge in this task is the significant difference between these EXO cameras and the Ego cameras. So the key here is how to inject this EXO video information into our ego diffusion model. And it's how to do this conditional parts. And to achieve that, we propose two designs, the EXO appearance encoder and also the EXO-to-ego transition player to provide the dense and spatial aligned features as guidance for our ego video generation. So we can first look at this multi-video EXO encoder in this orange box here. So for this multi-video EXO encoder, it's essentially a diffusion unit. The input would be this egocentric video frames as well as the camera poses, and we utilize these diffusion blocks to extract the dense and multi-scale appearance features from the egocentric views. And then we use these EXO features as the appearance guidance for our ego diffusion pipeline. Specifically for this ego latents here, we can catch this ego latents with these appearance features. And through the self-attention mechanism, this ego latents, it can attend to both itself as well as to these exocentric features. So the good thing about this data is that it can provide dense and multi-scale features through these different layers of diffusion blocks, but it has to rely on the self-attention mechanism to attend to the corresponding regions of the EXO frames. So which is still quite challenging because due to the difference between the EXO and the ego views. So that's why we propose our second design. We call it EXO-to-ego transition player. This is essentially a lightweight generalizable nerve, like pixel nerve. And we first pre-train this player using the EXO and the ego views. And during the training, this pipeline training, it can render these ego features and also render the ego pixels. So for this rendered ego features, it can provide a course guidance of how the scene would look like. So we concatenate these ego features with our ego latents. So this can provide the direct spatial aligned guidance about how the scene would look like for these ego views. And but the concept of this design is that this is a bit cost due to the limitation of the generalizable nerve. It's still quite challenging for them to handle the large viewpoint calculations. But the good thing is that it's a spatial aligned. So we think these two designs are for EXO encoder and this EXO-to-ego player. These two can complement with each other. So this provides dense features, but it's not spatial aligned. Well, for this feature is spatial aligned. It can be directly utilized by the concatenation, but it's not it's a bit cost compared to this EXO encoder. So these two can provide the dense conditions for our ego generation. And finally, we also introduce temporal attention layers in our diffusion pipeline to improve the temporal consistency for the ego frames. During the training, we first pre-train this EXO-to-ego player, and then we remove the temporal layers and only train these spatial layers. And finally, we freeze these spatial layers and only fine-tune these temporal layers to improve the consistencies. So this is the pipeline of our model, and for the evaluation, we mainly evaluate on the Ego4D dataset and also for the H2O dataset. For the Ego4D, we select 5 scenarios, including cooking, basketball, to will test CPR and bike. So this features more about the human-object interactions. And for each category, we train a separate model. So which means we train 5 models for 5 categories. For the evaluation, we follow the EXO-to-ego to evaluate on the unseen actions, unseen takes, and also unseen scenes. For unseen action, it's just the 20% test actions that are not seen during training. And for unseen takes, we randomly select some takes that refer to the complete human activity video. And for the unseen scenes would be the novel scenes that are not seen during the training. But for example, training on the Singapore and the test on the United States. So this provides the quantitative comparison of our method in comparison to these three baselines. Because we are the first one to achieve the ego-to-ego video generation, so we designed these three baselines: stable video diffusion, stable diffusion, and pixel nerve. We modify their input and output to make sure the input and output is the same with ours, and also fine-tune or train their models on the same dataset. So we can see that we achieve the best performance for unseen action and unseen take, especially for LPIPS metric. It's about 35% improvements compared to these baselines. And for the unseen scenes, it's very challenging. We found that all the methods, including our method, encounter the performance drops for the unseen scenes. And our method achieves the best performance for most of the metrics. So this provides the qualitative comparison for our method against the baselines and also for the ground truth. So for the pixel nerve, you can see that it's quite blurry because it cannot handle these large translations. For the stable diffusion, it cannot generate the corresponding backgrounds or human object interactions. So the best baseline would be the stable video diffusion.
One minute.
When we compare, so when we compare these two, we found that we can render more about the human object interaction details. And this is more about the unseen takes, and similarly will show much better performance than these baselines. And also for the unseen scenes, although we can achieve much better than these baselines, but we also notice a performance drop for these unseen scenes. And here are more results on the H2 dataset. It's an easier dataset, so we can also see that it's much better performance than the Ego4D. And for the application study, we found that our full model achieves the best performance. And when we remove the ego-to-ego pair, sometimes we notice it's get a better RPIPX metric. But when we realize it, we found that our full model still can generate more about like for this right human arm, our full model can generate the more accurate results than when we remove the ego-to-ego pair. And also for this ego-to-ego pair, we realized how the feature map would look like with our rendered ego-to-ego pair. It can provide the guidance of how the scene would roughly look like, very good enough to provide the condition guidance. Here are more demo results for this basketball scenario, including our method in comparison with these baselines. We capture much better than this baselines for this playing basketball, and also for these cooking demos. In our release supplemental videos, we provide many demo videos for these realizations. And finally, a quick summary about this work is that we are the first to achieve ego-to-ego video generation for the skilled human activities, and we designed a new diffusion-based ego video generation pipeline with two conditional modules, including diffusion-based ego encoder and ego-to-ego video translation prior. And finally, we can achieve much better performance with certified performance improvements for LPIPS. With that, thank you very much for the attendance, and very happy to take any questions.
Thank you very much. Questions? Let me start by one because I'm a bit confused. So do you know where the ego camera is? Do you feed that to your model?
Yes, we feed the camera pose to the model.
Where is that in your model diagram?
Yeah, we actually have two parts for this pose. Yeah, this is firstly in this pose, we inject this pose to the ego diffusion unit, and secondly for this ego-to-ego pair, because we need to render this ego feature, so we have to know where is the ego camera so that we can render the feature.
What if that pose isn't right? What if I give you a different camera location? Do you think this thing will work?
Yeah, I think this will work because this different camera location will directly guide these two modules.
Okay, but you haven't tested that. You haven't tested giving a different camera pose.
Yeah, no, we didn't test that.
Any other questions?
I have a quick one. So maybe I missed it, but did you try to input more or less exo cameras, and what happens when you, for instance, only feed one of them?
Oh yes, thank you for the question. So we actually in our camera ready model, we actually provide the application study for the different input EXO views, and we found that when we increase from 1 to 3 EXO cameras, the performance continuously increase, and it's it's almost saturated with the 3 or 4 EXO cameras.
Which probably are minimizing the occlusions in some sense. I guess that's
Yes, exactly.
Yeah, I was curious how much you're actually hallucinating. So do you know which of these pixels are visible in any of the EXO cameras and which are just, because you can figure out which of these pixels actually are visible in the EXO and evaluate only for those.
Yeah, I think that's a very good question. But in our model we didn't test this how the overlap between EXO and Ego views, and sometimes we found that so when we increase the number of views, we actually do not select the specific views. It's just the random samples of views. Yeah.
Great, thank you very much. New topic, so thanks for making rounds. We move now to the next talk, and that is by Feng. So.
Thank you, Emma. I will share my screen.
Let's try that. Yeah, we see your presenter mode. You might want to swap displays.
Yeah, great. Thank you.
No, we do see your presenter view. That's not what you want us to see. So go to the top and click swap displays. Yeah, fantastic. Now it's perfect. Go ahead.
Okay. Yeah. So, hello everyone. I'm Feng from UNC Chapel Hill. So nice to see everyone on the symposium. Today I will present our work for diff 3D aware diffusion model for 31st viewpoint translation. So this work is actually very similar to the one Jiawei presented like several minutes ago. So the difference between our work with Jiawei's work is we only input like one EXO view. And also our target is to train a single model. So like this is the input. We provide only one EXO view and also the camera pose to the model. Then we want to output the egocentric view of this particular person. So like this task can be applied to various applications, such as the immersive experience in AR or VR and skill acquisitions from an exocentric demonstration. So in this work, we leverage the recently released Ego4D dataset for this task. So it's a very challenging benchmark. As you can see, there are numerous objects, complex background, dynamic objects and scenes, and large view changes, and also like diverse scenes and data activities like in this dataset. And all of this pose a large challenge to existing methods. And the most existing methods are designed for novel view synthesis. And the two major types of methods are nerve-based methods and diffusion models. So, however, in our task, the nerve-based methods are difficult to optimize on the diverse and the complex scenes. And especially, we only provide one single EXO view as input. And for the diffusion model, so they can generate highly photorealistic images, but diffusion model do not care about the geometry. And in this work, we aim to develop a 3D aware diffusion model for this challenge problem. And this is our framework. So given an exocentric image, we first use a feature encoder to obtain the exocentric feature map. Then we apply a depth estimator to predict the depth map for this exocentric image. So based on this depth map, we can convert the 2D image into a 3D point cloud. And each 3D point is associated with an RGB color and a semantic feature. And then we use a point cloud rasterization technique to render the 3D point cloud from the exocentric view to the egocentric view. And then we concatenate this ego prior with the noisy ego view. So the noisy ego view is like standard input in the diffusion model, and to DIT, like a transformer-based diffusion model, and to add to denoise. And to further ensure the geometry correctness, we propose a 3D aware cross-attention layer, to inject the 3D information into the diffusion model. And next, we will talk about how we inject the geometry into the attention layer. So these are the equations. But if you if you remove the R, this matrix R, then it is actually the standard cross-attention. So for example, if R is an identity matrix, then it is a standard cross-attention. And we encode the geometry information into this matrix R. And the right figure is an illustration of how the rotation matrix R is calculated. So suppose the yellow vector is a query, like the Q in the feature map, and the purple vector is the key. And the R for this query key pair is a rotation matrix that to rotate the key to the query. So in this way, the similarity calculation in cross-attention is related to both the feature similarity and also the geometrical distances. And this is the quantitative results. And our method for diff outperforms prior method by a large margin on all metrics. So these are some qualitative results. So it's like compared with the nerve-based method GNT, and the 3DIM is a diffusion model, and our model performs much better than the prior methods. So this video is generalization to the unseen take. The scene is seen during training, but this take is not seen. And our generated video follow the camera trajectories quite well. So the hands and objects also align quite well with the ground truth. But you can see there are many flickerings between the frames. So this is because our model is actually an image-to-image model. So there's no temporal consistency right now. So this is another example. So let's see, when it generalized to the unseen scene, so this is much challenge because the entire scene is unseen during training. And you can see the performance drops actually quite large. But even you can see there are many flickerings. The view of our generated videos generally align with ground truth. In comparison, the 3DIM totally fails in this case. So these are some future work. The first, our work relies on the relative camera pause. So predicting the camera pause makes it more make it closer to the practical applications. And the second is our method is an image-to-image translation approach, and incorporating the spatial temporal cues from video and further improve the performance. And lastly, we train our diffusion model from scratch, and leveraging most large-scale pre-trained diffusion models can further boost the generation quality. So thank you. Any questions?
Thank you very much. Any questions? Let me try by asking, how much does the denoising, if you're providing us one version, right, that is one noise level. I'm assuming you're using the same consistent noise when denoising the video? The videos you're showing in qualitative.
You mean the noise in the input?
Mm-hmm.
So so actually during inference, we start from the pure Gaussian noise. And
But
then
is that consistent over time when you are showing us your final video? Is it the same Gaussian noise over time?
so like in different frames, we use the same Gaussian noise. Like
I'm wondering how much noise is left in the system because you're very much overfitting to the scenes, right? So if I feed a different Gaussian noise, am I getting how much difference there is?
so we didn't check, but like so right now the results like the noise are randomly sampled. So also like actually so our target is to train a model to predict the same results from different noise. So like theoretically like you randomly sample a noise, it will try to make it the same, the output is the same. So this is like
I agree. But the
yeah.
particular value of the diffusion model is that you will produce a different value with different noises, right? Otherwise, it's a deterministic model if you don't want the noise to make a difference, right? There is a question from Giovanni.
Yeah, I was wondering how do you choose the exocentric view? Was the one marked in the datasets as the best, or you try to, or is it random selected, or at what change if you change point of view with the different four we have in the dataset?
So yeah, very nice question. So like we randomly sample X of view like as input, like during training and inference. So like this is we aim to mimic the practical application, like the user may have their exo camera like anywhere in this environment. So like we use a single model to handle arbitrary exo cameras.
Okay, so a second question was about the distortion. I see the input, the exo input is undistorted, right? Is there any practical motivation to do this step or?
Yes, so like when we undistort the input and output, then the camera model, which like the camera model will become much simpler. Like the mapping from Excel to Ego view will be much simpler. So like if we want the distorted version, we can like distort our results again to make like distorted version. So this distortion and undistortion is related only to the camera. Like it can be a fixed set of parameters.
Okay, thank you.
Great, thank you very much. We move now to the third talk, and that's by Sagnik.
Yeah, I'll share my screen. Can you all see my screen?
We indeed can, and we can hear you.
Okay, thank you. Yeah, so hi everyone. I'm a PhD student at UT Austin where I work on multimodal 3D scene and human activity understanding. Today I'm going to present my recent work on language for weakly supervising view selection in multi-view videos. In this work, we tackle the task of view selection in multi-view instructional videos. By instructional videos, I mean videos that show a person demonstrating how to perform an activity. Such videos are usually used for instructional or in other words, educational purposes. Specifically given an instructional activity captured from multiple camera viewpoints, the goal in our task is to choose the most informative camera view with respect to demonstrating the activity. Being able to successfully solve this task can facilitate multiple applications like high quality human viewing and skill learning and preemptive single camera video capture in multi-view but energy efficient settings. Here we give an overview of related and state-of-the-art works. They can be put under three broad categories. The first one is temporal video summarization. The main difference of our work with this area is that while in temporal summarization, the goal is to create a temporally sparse summary. Our goal is to create a temporally dense but spatially sparse summary of multi-view videos. The next topic is active next view selection. In this line of work, the goal is to train an embodied agent to smartly position its camera for capturing informative views for solving tasks like object or scene recognition. On the other hand, our task involves selecting a single view from pre-captured multi-view videos. Finally, probably the most related line of work is automatic cinematography. However, these methods either require large-scale manual labels for learning view selection, or they tackle virtual videos and specialized settings. In contrast, in this work, we tackle instructional videos, and more importantly, we focus on a label scarce setting, as I'm going to discuss next. Specifically in our task, given a multi-view instructional video, our goal is to train a model for choosing the most informative view at each point in time in the video in a setting where there are no manual labels to supervise this training. Note that in our label scarce setup, we assume access to dense text descriptions of the activity happening at different points in a video during training. We call these text descriptions narrations henceforth. Our core idea for designing such a method is to leverage the narration text for providing weak supervision during training. Specifically, given a short clip from a multi-view training video, we first use off-the-shelf captioning models to predict a caption for each view in the video separately. Next, we compare each of these predicted narrations with a independent ground truth narration, which, as mentioned before, is available with the videos in our setup, and we score each view on the basis of how close its predicted narration is to the ground truth. We then pick the view with the highest score as a pseudo label for the best view for this clip. Finally, we generate a set of pseudo labels by running this pipeline on other training clips and use them to train a view selection model. At a high level, our method is composed of a best view pseudo labeler and a best view selector. For generating pseudo labels, we begin by using a set of off-the-shelf captioners to caption each view of a multi-view clip. Next, for each captioner, we compute the score of each view by comparing the narration predicted from it with the ground truth narration and use these scores to rank the views. Next, we aggregate the view ranks across the different captioners. Specifically, we discard all views that are not ranked the highest across all captioners. We use the remaining views to create our pseudo-label set. Note that by using multiple captioners and enforcing complete consensus among them for producing pseudo-labels reduces the effect of captioning noise by our off-the-shelf captioning models. Our view selector has two components, a view classifier and a relative camera pose predictor. The classifier begins by extracting a fine-grained patch-level feature from each view and then projects these fine-grained features into more coarse-grained ones for outputting a best view estimate for the clip. We train our view classifier using a new loss formulation that accounts for the potential presence of multiple best view pseudo-labels for a certain clip. Specifically, our loss formulation encourages our model to predict as its estimate the pseudo-label it finds the easiest to predict, or in other words, is the most confident about. However, just using the classifier can hurt generalization, as our pseudo-labels may not be sufficiently discriminative in certain cases due to the very nature of our captioner training, where the captioners learn to map all views to the same view-agnostic ground truth narration. To prevent this from happening, we train our relative camera pose predictor, which improves the view specificity of the classifier's visual features by using them to simultaneously solve for the task of relative camera pose prediction. Specifically, in our pose predictor, we take the classifier's fine-grained visual features for all possible view pairs and pass them through a feature projector and a classification head, which produces the relative camera pose estimate for each view pair. We train the pose predictor with an average cross-entropy loss between the relative camera pose ground truths and their estimates, where the average is computed over all view pairs. We train and evaluate using two multi-view instructional video datasets. The first one is Ego4D. It comprises 5 camera viewpoints. One is an egocentric view and captured using a camera head worn by the person demonstrating the activity, and the other 4 are exocentric views captured by stationary cameras placed around the scene. Besides, it consists of both physical scenarios like basketball or rock climbing and procedural scenarios like bike repair or cooking. Finally, its narrations are temporally dense and free-form text descriptions of the activity happening at different points in a video. Our second dataset is Lemma. Similar to Ego4D, Lemma consists of a single ego view provided by a camera head worn by the instructor. For exo views, it has a single stationary camera placed facing the side of the activity. Unlike Ego4D, Lemma only has videos from household activities like watching TV or making cereal. Moreover, its narrations, despite being temporally dense, they just list action verbs and objects for a predefined vocabulary. For our metrics, we perform both automatic evaluation and human evaluation. For automatic evaluation, we use an off-the-shelf video captioner to estimate the narration from a predicted view and compare the predicted narration with the ground truth narration using both captioning metrics and metrics that capture action and object recognition accuracy. For human evaluation, we ask human raters to compare the view predicted by our model with that predicted by a baseline. These are our results from automatic evaluation. We compare against multiple different baselines. The first group of baselines is naive heuristics, which help test how challenging our task is. The next set of baselines uses priors like maximizing the visibility of hands and interacting objects, or that of the body of the instructor for driving view selection. These baselines test if such priors are enough for solving our task. We also compare against a state-of-the-art view selection method that uses the extent of foreground object and pixel visibility in a view to choose the best view. Finally, we compare against a baseline that selects the view that produces the longest narration as the best view. This is an alternative but a more naive way of using language to guide view selection. However, note that this model assumes access to a captioning model for narration prediction at inference. Our model outperforms all baselines on both datasets and across all metrics. And these are our results from human evaluation. We conduct this evaluation for assessing our model on two fronts. The first one is pseudo-label quality. In this assessment, we compare the human preferences for the best and the worst views according to our pseudo-labeler. In the second one, we compare the human preferences for the view selected by our model with that selected by the two best performing models from our automatic evaluation. In both assessments, our model selected view is preferred more by humans. Here is a qualitative view selection example from the Ego4D dataset. Note how our model prefers the ego view when the relevant body parts and objects are not visible in an exo view, for example, the instructor trying to grip or hold. On the other hand, the model chooses an exo view when the full body is involved in an action, for example, the instructor falling off the wall, or when the entities relevant to the action are outside the field of view of the ego camera, for example, the instructor placing their foot on a hold. Here is a similar qualitative example from Lemma. Note how our model prefers the ego view when the relevant body parts and objects are not visible in an exo view, for example, the instructor pouring milk or cereal. On the other hand, the model chooses an exo view when the relevant body parts and objects go out of the ego view, for example, the instructor closing the fridge while their head is in motion, or when the entities undergo vertical motion, which is not properly captured by the ego camera. For example, the instructor placing a bowl or cereal box on the table. In future work, I plan to tackle preemptive view selection for using such a view selection system in energy efficient settings, and also learn human view choices from large scale in the wild video datasets like How to 100 Million for performing view selection that is more closely aligned with human preferences. Thank you.
Great, very nice work, very nice presentation. And Tonina.
Yeah, thank you. Thank you for the presentation. I have a question. So I could not help but notice that in the qualitative examples, so the qualitative examples looked maybe less human readable than just looking at the ego view. So every time that you have this switch of camera, in some sense, I got confused. At least maybe it was just me. I don't know. And I wonder if by doing this, we are maybe capturing a bias of the current models for captioning that really prefer the exocentric views, even if the ego views actually conveys a lot of information. And so the switch from one camera to another one, like from the ego to the exo, most of the time is beneficial because all these models that are out there have been trained on exocentric views, and so they have a bias rather than we are selecting the most informative view. Maybe it's just more a comment than a question, but I don't know. What do you think about it?
Yeah, that's a good question. But the thing is that we retrain the captioning models on each of these views. So it's like if the information is captured more in the ego view, it should choose the ego view. But then the fact that we are grounding it in narrations is kind of might like bias the model towards the aspects of the activity that are captured in the narrations. But we try to take care of that by like evaluating using human raters. I mean, it doesn't take care of it at the training level, but we at least try to make like the evaluation more unbiased.
Thank you.
Any other questions? In the meanwhile, I wanted to question your notion of that this is a view agnostic narration. There was a slide that was referring to our narrations as view agnostic.
Yeah.
As I understand the term agnostic, I think view agnostic implies that whatever the view was, I will produce this narration. And I don't think that's true.
No, I only call the ground truth narration as view agnostic because
Yeah, I'm questioning the ground truth narrations being view agnostic. Yeah. So the
Yeah.
ground narrations are narrations that people produced, right? But they are not necessarily present in every view. And accordingly, they can't be the right narration from every view. So I'm just questioning the term view agnostic. They're the narrations we have, and we probably don't know what views. I don't know. Has the narrators seen all views?
Yeah.
They
They
have.
saw the collage of
But you don't know what views they've used to give that narration. But that doesn't make them view agnostic, don't you think?
Yeah, true. I mean, they might have focused on a few views more than the others to produce the narration, but what I meant was like it's like holistic. Like they look at all views, and
Yeah.
so whichever views they found to be the most informative about the activity, they use them to produce the narration. That's
Yeah,
what
yeah, it's just a risky term, right? Because
Yeah.
it implies that from any view you can produce this narration. And that's not
Yeah.
really correct. And then can we look at the numbers, the ego only versus and that's something we probably knew like all the time is ego is very hard to beat, right? So so clearly, yeah, I'm wondering if that's a bias in our narrations, that our narrations are ego specific. What if we actually narrated only from EXO? Then the numbers will switch, right?
Yeah, could be. Yeah, I mean, this is the data we had, so we could only test with it, but yeah, could be. And I think it also depends on the scenario. Like, for example, for cooking, I think ego does the work most of the time. So it's also like scenario specific.
And being fascinated about audio, I wondered whether audio would have been enough to give you the right view, like which view, like ego versus exo. Maybe it won't tell you which exo, but it might tell you that the action you're interested in is out of view.
Yeah, but for that, I mean, yeah, like I think Ego4D supports multi-channel audio, so you could maybe use that, but just from the semantics, I don't know, they might sound the same from all views. But yeah, if you have like multi-channel audio, then it has spatial information in it, so that would.
Any final questions for Sagnik? Otherwise, thank you very much. And we move to the last talk in the view selection and generation session, and that's by Camillo.
Yeah, share the screen.
Yeah, can you share your screen? We can hear you.
You see it?
Coming, it is there. Yes, go ahead.
Okay, so hello everyone, I'm Camillo Quattrocchi from the University of Catania, Sicily. And today I will present the work titled Synchronization. So we need exocentric to egocentric transfer for temporal action segmentation with unlabeled synchronized video pairs. And this work was presented in ECCV 2024. As we know, transferring knowledge from one domain to another is still an open challenge. Specifically, we know that a system trained on third-person data called exocentric data will struggle to work on data acquired from a first-person perspective using wearable devices that are called egocentric data. For example, a company may have collected exocentric data from fixed cameras and trained their temporal action segmentation models in order to monitor the production processes. At some point, for example, the company might decide to purchase wearable devices to acquire egocentric data and adapt the new algorithms to the new data. This process is not simple, as we know, as this requires acquiring new data, labeling it, and retraining the models. As we know, labeling video data is a time-consuming and resource-intensive process. And for this reason, in this work, we propose an adaptation methodology based on unlabeled ego-exo video pairs that leverages the technique of knowledge distillation. The main goal of the methodology is to adapt a temporal action segmentation model from the exocentric view to the egocentric view using unlabeled ego-x video pairs. The methodology incorporates a combination of feature extractors, namely TSM and NeurIPS, and a temporal action segmentation model called C2FGCN. Within the proposed methodology, knowledge distillation used at two different levels. At the feature level, where we aim to extract the same feature from the feature extractor regardless of the ego or X view, and at the model level, where we aim to align the internal representation of the two ego and X models. The dataset used to validate our methodology share the characteristics of being procedural video dataset. And the first, Assembly 101, contains synchronized Ego-Exo videos of user assembling toys, while the second, Ego4D, contains a video of user performing various procedural activities from a different point of view, including the egocentric one. Okay, here you can see the pipeline of the proposed methodology. Initially, at step 1, a pixel camera captures third-person data, which is then temporally labeled and used to train a temporal action segmentation model called EXO model. Then at step 2, egocentric data is acquired from wearable devices. When these new data are used with the previously trained model, the resulting temporal segmentation obviously will be poor. At step 3, the adaptation phase from EXO to Ego view begins, and specifically two synchronized Ego and EXO view streams are captured. And these new video streams will not be labeled at all. And then defining the old EXO model as the teacher, we define a new student model called the Ego model. And during the adaptation phase, the video streams are passed to the corresponding model, and the prediction of the EXO model are used by the Ego model through knowledge distillation techniques. At step 4, the last step, finally, we can see the new Ego model making correct temporal prediction, even though it has never seen any labeled egocentric views. During the distillation process, the student is optimized in order to mimic the outputs of the teacher component. This process is carried out using an adaptation set composed by synchronized Ego-X video pairs. This is important, no exocentric or egocentric labels are used at this time, with the only supervision being given by the exocentric videos passed through the fixed teacher. We consider two adaptation steps that can be either included separately or combined: feature distillation and temporal action model distillation. In feature distillation, we encourage the student model to extract from the egocentric videos a representation similar to the exocentric one extracted by the teacher model. While in the temporal action segmentation model distillation, the aim is to distill the student model to make its internal representation similar to those extracted by the teacher model on the paired exocentric video. Okay, here are the results of the Assembly 101 dataset. For each feature extractor, experiments were conducted using the two distillation methodology, individually or combined. In general, the model using feature extracted with NeurIPS performs better with any level of distillation used, achieving 15.99% improvement in terms of edit distance compared to the model that does not use any adaptation techniques. Even the model that uses the feature extractor with TSM showed good performance, achieving an improvement of 14.86%, also in this case in terms of edit distance. Here, the results on the Ego4D dataset. Experiments refer to feature extracted with Omnivore, and here we explored both the EXO to Ego transfer and the Ego to EXO transfer, achieving a best results of a 4.44% improvement in terms of edit distance when we transfer from the Ego view to the EXO view, while we achieve an improvement of 3.32% when we transfer from the EXO view to the Ego view. Probably the smaller gain compared to the experiments on the Assembly 101 dataset is due to the higher complexity of the Ego4D dataset. In order to validate the methodology presented in this work, we presented some ablation. For example, in adaptation number 1, we performed experiments varying the ECCV usage due to the nature of the considered datasets to be multi-view. In adaptation number 2, we performed experiments with different amounts of labeled synchronized EgoXV universe for knowledge distillation. In adaptation number 3, we tried to different sets of layers. This is because the temporal action segmentation model that we used, that was C2FTCN, internally produced different representation levels of the output, and we try to not use all of this for this adaptation experiment. In adaptation number 4, we performed experiments with fixed amount of data in order to understand if the improvement comes from the amount of data or from the EgoXO correspondence to the distillation. And last, in adaptation number 5, we tried our methodology in order to understand if it is applicable in other tasks. For more details about the evaluation, I invite you to read the paper. Okay, in conclusion, the main contribution of this work is the development of an innovative methodology for adapting from the exocentric to the egocentric view for the task of temporal action segmentation, demonstrating the effective contribution of knowledge distillation when using synchronized ego-exo universe. The results shows that the proposed method achieve comparable performance with supervised approaches trained on all the level of the egocentric data without using egocentric labels. Thank you very much.
Thank you. Any questions? Let me ask for one. So there is always this question of, are the views redundant or complementary, right? So here in the distillation, you are looking at the redundancies between the views, because you're assuming there is some information in one view that you can distill for the other. But then there is the other dimension, which is what's unique about every view, right? The actual thing that is not in the other view. And how do you see these two dimensions interplaying? Do you think one model could be used to distill but also keep the uniqueness, or these are completely different tasks to be considered independently?
If I understand good, well, you mean that if I use the previous, the new model, the distilled model for the exocentric data, right? Obviously, the performance are poor. We tried to these models with the older exocentric data and are poor the performance, yeah.
Right. So maybe what's next? What do you think we should do next in this direction?
Actually, we are working on extension of this work. We are extending the comparison with the state of the art on this work. We are adding data sets in order to validate more the methodology that we presented, and we want to exploit if we can use the feature extracted from Day2 in a better way, because we didn't fine-tune Day2 because it's huge, it's complex, and we want to try to use spatial information maybe from Day2.
Any more questions for Camillo or any of the speakers in the first session? The moment of silence. If not, I'd like to thank all the speakers. We do have in the schedule a 25 minutes break, so we're back at 25 past. Thank you very much.
I have to re-enter everything here. And then hello. Sorry, I had to rejoin with camera.
Okay. Welcome back, everyone. This is the fourth and last session in the symposium. We will be having concluding remarks at the end, so stay on. And this session is about body, pose, and expertise. We will be starting by a talk for UC Berkeley for a work coming to ArXiv soon. And then University of Andres work to be presented at WACV 2025. Sorry for my mistake, it's last year, it's upcoming year. And then two works from one from UC Berkeley archived and one from UT Austin archived. And we start with Leah reconstructing people, places, and cameras.
Hello, everyone. Nice to meet you. I'm a postdoc at UC Berkeley with Jitendra and Anju, and we've been working a lot on reconstructing people and cameras. And Brent is also here, who's a co-author on this work. Yeah. So let me give you a little bit of motivation why we want to do this. Humans are social people, right? We interact with the world, we interact with other people around us. And these interactions are super important because they let us navigate this world, like physically, but also socially. Okay. And there's a lot of evidence for this, like for the importance of our contacts with other people coming from psychology, actually. So this is a very extensive list. I just picked 4 things that I found most interesting and hope you also find them interesting, and I can catch you more to work in this field. So the first thing is it starts in early childhood, when parents and children, and especially the contact between them, establishes bonds, and it is actually linked to immediate stress reduction in the children. So that's amazing, right? Like your baby cries, you just hold it, maybe doesn't stop crying, but at least it's a little less stressed. And then this goes on into adult life. So doctors who touch their patients are considered more caring, and it reduces also the stress level in patients, and they even have better medical outcomes. I think that's incredible, right? It's not just our feelings that are affected, it's like even our health that is affected by contact with other people. And then the third point here is, well, maybe that's the real world, but even in the virtual world, we consider agents that incorporate touch with other people as more human-like. So it's something very important. And to me, this is already convincing. Now, maybe you're not a parent, you're lucky you never got to see a doctor, and you don't care about VR. So I want to bring up one more point, okay? And this is called the Midas effect. It was an experiment run by 2 psychologists in 1984, and it goes like this. So they had people in a restaurant, and then they instructed the waiters to not touch their customers or to slightly touch the shoulder of their customers. And now guess what happened? 20% more tip. Okay, so the 20% is made up, but the touch led to an increase in tip. And they concluded that this is like something, a pattern in human behavior, and that interpersonal physical contact leads to an increase in generosity. And actually, this was replicated many times. So not just in like a restaurant setting, also people asking others for favors, like walking their dogs or getting on the bus for free. So contact has not just an impact on our internal states and feelings, it also has an impact on our wallet. Now there's one big problem with this entire setting. I guess you can already see it. Super small sample sizes. Like all these studies in psychology that we're running, they're, 100 participants. Maybe we get 400, but it's super challenging to get these people into, a lab setup and study them and instruct them. And I think if we compare this to, the data set sizes we're using to train our models, it's tiny. And I think this is really where we as a field can step in and contribute methods to advance research in this area. All right, so how can we do this? Well, gladly there is YouTube and there's lots of data in the internet, right, of people interacting with each other. There's surprises, right? So it's even a little natural, weird handshakes, people hugging, arguing. So we do have all this internet data, but understanding or reasoning about what people are doing in these videos, that's quite challenging, right? Like, what do we need to know? We want to know their 3D physical distance, right? The proximity between people. We want to know their interactions with the scene, and we also want to reason about the contact and what they're doing. Okay, people have tried doing this, but processing long videos and understanding them is still challenging. So I want to break it down or make it a little bit easier. Let's consider this setup where we have people interacting with each other, like these 3 guys building a Lego or Duplo castle together. And these are time synchronized images, right? Recording the same scene. And we also assume that the identities of people across views are known. Okay, so how can we, are known. So how can we process this data? There's very recent methods like Duster that's data-driven structure from motion. And these methods take as input a set of images and output a 3D scene. Like in this case, it's a 3D point cloud, and also the camera poses for each of these input images in the scene. Okay, there's just one problem, okay? When we look closer, the humans are not really reconstructed well. So the back in this example is entirely missing. And sometimes it's even worse. So in this example, you see like a person, this is again like 4 images of the same scene, time synchronized. And then you see a person here in the foreground, really large. But when we look at the reconstruction, the person is completely baked into the scene, right? So it's pretty much part of the floor here. And that's a problem, right? We cannot just take the pixels of our input images here and reason about the location of the person in the scene. Now, what else can we do? Well, there's a second big branch of research going on that's estimating human poses from images. Okay, this is a paper from ECCV 23. It's called HMR2. And here we get the local pose, like the body pose of all people in this video, and also a rough body shape estimate. And it's incredible. I think when we look at these results, it was really nice to see how well we can actually estimate body pose just from a video. But there's also a problem. This is just in the camera coordinate frame. So all these people, like even if you see them projected into the video, in 3D, their distances are not meaningful. Okay, because we just estimate each person for themselves. This is a little bit of background for those who are not familiar with Simple.
2 more minutes, so maybe you need to plan accordingly.
Yeah. So for those who are not familiar with Simple, so what we do instead, is like estimate the parameters of a body model, okay? And then we can take this body model and create a 3D mesh. Now, how do we bring this together? Like that's the output here. We have people in the scene, okay? The first thing we do is we process a lot of videos. Like we estimate 2D joint locations with VIT pose. Maybe you know OpenPose, it's kind of similar. and HMR2 and Duster for the scene. And then we place the person in the world with the Duster focal length and the height of the person. Okay, and then we use the human as a reference object to estimate the camera positions around the person and scale the Duster cameras, which are not at metric scale, to match these human-centric cameras. All right, then roughly we can place people. Okay. And then all we need to do is a joint optimization over the 2D key points with a reprojection error and the scene alignment loss, which is a global alignment loss from Duster that, you know, brings all the pixels into a joint 3D space. And doing this now places people in the world. And it's incredible because they're like, we saw this, we were so excited. They're actually touching the floor and we're not incorporating any specific contact terms here. So we did evaluate this on Ego humans, okay, and the pose location of the people was better, but also the camera poses were better. Okay, this is another example. And then we run it on Ego4D. And this is one of the bike shop scenes. Maybe you've seen it. And yeah, we get, you know, on the right side, the people located in the scene. So we have more dense information about the body poses. We know the joint angles. And we can hopefully use it to study people better. This is a dancing sequence. Yeah, here in the kitchen, right? So yeah, it just aligns with the human point cloud roughly. Yeah, even like object interactions, right? This person like playing the piano. And we're using all cameras here. Like we just use the cameras available. And one of the biggest problems is, let me come to those. We'll skip this. Oh, sorry. So one of the biggest problems for us is actually re-identification of people across frames, because we are assuming this is known for now. But especially in these basketball scenes, for example, this was really hard because there's so many people running in the background, and eventually we want to reconstruct all people, right? But we're just focusing on, for Ego4D, on the main person right now. Yeah, so if you have questions, I'm happy to.
Thank you very much. Questions? I'm trying to see whose hand is up. Sorry.
Mine.
Go ahead. Yeah.
Hi. I have a question. How does your performance changes when you have only 2 cameras versus 5? Like, do you get better positions when the more cameras you have? I mean, I assume yes, but could you talk a bit more about it?
Yeah, we evaluated this in we have a table in our supplementary material. Yeah, so it improves, like if you have more cameras, that helps, and then the reconstructions are more accurate. We also found it's quite important that there's like good coverage of the scene. Like this definitely helps to get better reconstructions. Yeah.
Any other questions?
Maybe I can add to this. We had another experiment where we saw that, you know, more people actually help too. So between like a single person and I think Ego humans, which we evaluated on, has like 5 to 7 people, it also improved.
Great, thank you very much. We move to the second talk.
Yes. Let me share my screen. So I think you can all see my screen and hear me well, right? Okay, so I'll start. Hello, everyone. I'm Maria. I am a last year PhD candidate at Universidad de los Andes in Colombia. And today I'll be presenting my most recent paper titled EgoCast, Forecasting Human Proprioception from Egocentric Data. This work is done in collaboration with Google DeepMind in Zurich and will be presented at WACV next year. So let me move. Yeah, I think you can see it now. So for context, let's start off talking about embodied AI, which is creating systems that can interact with humans and learn from a physical environment. So while traditional AI approaches would operate solely in the digital space, with embodied AI, we aim to bridge the gap between the digital and real-world applications. Some of the real-world applications that we can have are things like medical analysis, sports coaching, and having AR systems that can help us navigate our daily lives. So for example, imagine that we have a virtual assistant that can help you learn how to play tennis like a pro by showing you the correct pose that your hand should have for a tennis swing, as you can see in this video in the right. So in order to create the methods that can help us understand the world in such way and to bridge this gap between what's virtual and what's real, we need to provide them a sense of how our body interacts with its surroundings. So one of the ways to provide models with this information is through visual inputs, and another one is through body pose. So full body pose estimation gives us the information about how we're currently interacting with our environment, whether we're holding an item or not, whether we're sitting in a chair or standing up. And forecasting future poses gives us insight into the intended actions that a person might have in the future. So if I'm going to move to the next room, will I need my lights to light up at the moment that I enter? Or if I'm going to take something for my recipe, should I check if I'm going to grab it in the future, in the close future or not? And so with this in mind, we wanted to use Ego4D as a test bed to study both pose estimation and pose forecasting. So in the pose forecasting task, let's first talk about why do we mean by it and how do we define it. So given an input of a 3D head-mounted camera location, which in this case are the ARIA devices, and the visual input of an RGB egocentric video from the past, our goal is to predict the future body poses and trajectories that a person might have for up to 5 seconds in the future. So this task formulation first is a bit different from the previous state-of-the-art methods that deal in forecasting. First, because we never assume that we have ground truth past poses. So you can see here in this orange line that resembles the input that we have, that we only would have the trajectory from the, in this case, from the ARIA device, or well, the head of the person, but we will never have access to the ground truth past poses because it's not what makes sense within the environment and well, the problem that we're solving. And the second one is that we are trying to evaluate how well or how bad do our methods do performing forecasting up to 5 seconds in the future at 30 FPS, which is way more frames than past forecasting methods used to predict. We would have something like 10 FPS, 10 frames at most for future prediction. So how do we tackle this task? We divide it into two parts. So the first one is current frame estimation, in which, given the information that I have from the past, I want to know where my full body pose is right now. So we create a dual stream method that processes the 3D camera locations through a location transformer encoder. And also we have a visual stream that processes the egocentric video. We use a pre-trained visual encoder and then we fine tune it. The pre-trained visual encoder is based on EgoVLP version 2, which is a video language pre-training approach for egocentric videos. And then we fine tune it with the Ego4D data. Afterwards, we concatenate both streams of representation and feed them to the motion decoder that gives us the 3D positions of all the joints at the current time step. When we have the positions at my current time step, then we're going to use those as input for the forecasting module. So here what we're doing is that we're predicting the full body pose for all of the previous frames, and we're passing it to a modified version of what we had in the location stream, where we will include an adaptive pooling layer to model sequences of different length so that we can adapt when we don't have as many past frames as we would like to predict in the future. And then finally, our output are the 3D joint locations for the full motion sequence. As you can see here, we adapted depending on the length of the forecasting sequence that we want to have. So for the experimental framework, we use the Ego4D dataset, which, well, all of you know and are familiar with. But the important part that I want to highlight here is how we're using the Ego4D dataset for pose estimation, which was one of the interesting parts that we collected. And well, here we have more than 100 million individual key points annotated for in the 2D images. And then when we project them back to 3D, well, we still have a lot of information in video. And another part of the experimental framework is that we use the standard mean per joint position error to compare the difference between the ground truth and the prediction. We are not assuming that they are in the same, that we are not translating the prediction to the ground truth to evaluate it, but just seeing how well our model predicts with all of the limitations that it might have. And then we also create a curve of the forecasting seconds versus the mean per joint position error and compute the area under this curve to measure the overall forecasting performance of each method. So the lower the area, the better the performance, as we're talking about errors here. And now going on a bit about the results. So first, let's talk about our results on current frame pose estimation. And we have the baseline methods from Ego4D in the Ego pose task. And we also tried, so the last one, that's the location base, would be the equivalent of only using one of our streams for predicting the current frame estimation. And we also tried a different approach, which was only using the egocentric video as the input. And here we can already see that only using the video is getting better results than only using the area location. This makes sense because we have more information to base our predictions off. And then when we're using both streams of information, the visual and the proprioceptive stream, we get significant and significant reduce in our errors for all the categories and the average. And what I'd like to show you are some interesting examples, visual examples. So here on the left, what we would have is the input video that the model is seeing, and we will also have the position of the area. And then on the right, we have a 2D reprojection of our 3D predictions for the ground truth, for an approach for forecasting in which we are not using the visual cues, and then a forecasting approach in which we are using the visual cues. And you can see that our pose estimation is way better when we are using the visual cues. It can predict things like putting the hands up or doing some movements that you can actually see them in our egocentric video. So we thought this was very exciting. And another one here, for example, is that when you're not using visual cues, the model defaults to predicting that the person is standing up, because most of the data includes people standing up. But then when you add the visual cues, as you can see here, there are some signals that can tell the model that the person is actually sitting down, that you can see your feet and different type of configurations. So our method that does use visual cues starts to predict that the person is sitting down. And now talking a little bit about the results in forecasting, we see that when incorporating both streams of information, the visual and the proprioceptive one, we are able to reduce the error in all of the forecasting seconds. And something that's also interesting here is that we wanted to see how far are we from achieving an accurate forecasting, let's say, with the methods that we have now that are the state of the art for current frame pose estimation. And for that, we also, created an oracle that assumes that we have the location fixed and we're only evaluating whether our positions are good. And if our location is the same as the ground truth, we would be at the tens of errors, which is very low. So this suggests that where we should be focusing next is in improving how we're predicting where our poses are located in the 3D space rather than the pose configuration, because that one, the problem is already advanced, I would say. These are some examples on the forecasting results for 4 seconds in the future. You can see that the further we go, the more the prediction degrades, but it still tries to keep the trajectory somewhat similar. And then to conclude, we're formulating a new way to study the pose forecasting benchmark for in the wild poses using Ego4D. And we expect that this can be useful for other people. If you have any other questions, you're invited to read the paper or discuss more. Thank you.
Thank you very much, Maria. Very interesting. Is there code and models coming soon?
Yeah.
Yeah. Can I ask about this Oracle thing? Because aren't you then trying to solve SLAM? Aren't you actually doing... Because if you say this is the hardest task, or this is like a significant part of the error, which is estimating where the camera poses, right? That's what you call the Oracle.
Yes, in the future.
Oh, in the future. I
Yeah,
see.
the problem is that it's in the future.
I see. But seems to be flat over time, not getting worse. Isn't that odd? Or am I
Yeah,
missing-
so what
Maybe I haven't understood
So-
Oracle.
So yeah, what we're doing in the Oracle is that the ground truth poses, we're assuming that our prediction is always in the position that the ground truth pose also is. So if the person is moving a lot, our ground truth are also moving a lot. It's moving exactly where the person is. And the problem here is that we cannot assume that we have SLAM, for example, because we are trying to predict it up to 5 seconds in the future. What I think the reason is for it to start to sort of plateau up until 3 to 5 seconds is that the movements that people are doing are not being so far ahead. So you go up until a point in 3 seconds, but then you're staying there. So the movements are not being too far. So if we had something like a person is walking down or running through somewhere, maybe in 5 seconds, you would still see a lot of the difference.
Any other questions? Yes, thank you, Maria, very much. Next is
Me, I think.
Brent.
Yes.
Estimating body and hand motion in an ego-sensed world.
Yes. Very exciting. Okay, let me share my screen. Is this visible?
Visible. Absolutely, yes, and we can hear you.
Okay, great. Yeah, so thanks so much for having me. Today I'll be presenting our work on estimating body and hand motion in an ego-sensed world. Okay, so in our work, we're studying this problem that I personally find very exciting, where we're trying to take these egocentric inputs that we have in data sets like Ego4D or Exo4D, and we're trying to map them to estimates of the wearer's body and hand motion. So concretely as inputs, we're assuming we have the SLAM poses as well as ego video. So here's an example of me walking through our office, interacting with this coffee machine. And then we're trying to estimate both the body pose as well as the hand pose of the wearer, all in the allocentric scene coordinate frame. So that includes this walking motion, as well as things like, the hand interactions with the scene. Here I'm using the coffee machine. So to address this problem, we are proposing a method that we call EgoAllo, because it's taking these egocentric sensing inputs and then bringing them into the allocentric coordinate frame in the form of 3D human motion. Okay, and so to present our method, I'm kind of just going to break it up into 2 high-level steps. The first is we're going to learn a generative prior that's conditioned on head motion. So we're going to train this prior on a mass similar to a couple of prior works like Ego and Bow diffusion, where as inputs, we have these SLAM poses. We're going to use this to condition a diffusion model that's going to give us local body pose as well as the person's height and hand parameters. And then once we have these local bodies, we can then align them back to our SLAM poses to get body parameters as well as height and hands all in the world frame. Okay, and this is going to look very similar to the final output that we actually want from our method. And so to just show an example of what we have so far, if we just run the sampling procedure condition on the input SLAM poses, for our method, we get something like this. Where on the left, I'm showing the SLAM pose that we're getting from like the ARIA glasses in Ego Exo4D. And on the right, I'm showing the body estimates that we get from the diffusion model. Okay, so that's step 1. Step 2 is we're going to go take the system and then try to improve the hand estimates that we get from it. Where here, our diffusion model is giving us hand estimates, but they're kind of just hallucinated because all we're doing is conditioning it on SLAM poses. So to do this, we're going to take the egocentric video and run a very simple off-the-shelf hand estimator. In this case, we're using Hammer, and then try to align estimates from our diffusion model to these hand estimates using this guidance procedure, where during sampling, we're going to alternate between doing denoising, so passing estimates through our learned prior over human motion, and this guidance procedure, which is an optimization process that takes whatever our denoiser gives us and tries to minimize some hand as well as foot skating losses. Okay, so when we put this all together, our system will give us something like this, where here's me again in our office, and we can get both an estimate of the body motion as well as what the hands are doing as they're interacting with the scene. So here I'm grabbing a doorknob. Okay, so for the rest of the presentation, I just wanted to touch on 3 things that we found mattered when building the system. The first is how we condition the diffusion model. The second is how our system can help resolve ambiguities that we get from standard off-the-shelf hand estimators. And finally, just like an implementation note on how we make the guidance optimization more efficient. Okay, so for number 1, how should we actually condition on slam poses? Where we want to take these input raw slam poses and pass them to a diffusion model, right? And one thing that we observed early on in the project is we ideally don't want to just use absolute poses because they're actually always defined with respect to some world frame, right? Where if you take slam poses, they're going to be transformations between the local device pose and this world frame. And the problem here is that this world frame definition is totally arbitrary, where we could take this world frame and rotate it, flip it around, or we could shove it to the back of the scene. And in all these cases, the human motion is the same, but we're going to end up with very different looking poses. Okay, and that might stop our model from generalizing very well. And so this is something that we can concretize as what we call spatial invariance, which is just that our head motion conditioning should be invariant to how you choose this world frame. Okay, and so this is something that prior works have noticed, and one strategy that's emerged is to take these full sequences and then canonicalizing them by aligning them to the first time step. So here I have the same human motion sequence as earlier, and we're going to take the whole sequence, and instead of expressing it with respect to some world frame, we're gonna define a frame underneath the first time step and define every single pose relative to that. And this is nice because it removes dependence on the world frame. But one thing that our work notices is that if you do this process, you're actually introducing another sensitivity, which is a sensitivity to time. So if we consider 2 slices of the same human body motion, right, we're going to take this same body motion and just slice it in 2 different ways. If you actually align each of these 2 slices with respect to the first time step, you actually once again end up in the situation where even if you have the same body motion, which I've circled here on the left and the right, it can look very, very different in terms of the head pose when you pass it into the network. Okay, so in the end, what we actually want is 2 invariances. The first one is spatial, which is basically robustness to how you shift this world frame. And the second is temporal, which is robustness to how you choose to slice your sequences. And so in our work, we propose a different way to condition these models where you actually define 2 types of poses. One is a relative pose. So that's how this head pose moves between time steps. And the second is what we call a locally canonicalized head pose, where you define a canonical frame on a per time step basis and then express your head pose relative to that local canonical pose. And this is very nice because it, first of all, fully defines the motion. Second of all, it's spatially invariant. It doesn't matter where you place that world frame. And then finally, it's also temporally invariant in that you can slice these sequences however you want, and you still end up with the same representation. And so we ablated this fairly extensively in our paper. We found that it can explain like a pretty large difference in estimation error. So we have the 2 types of invariance here in the middle. And you can basically see when you have both these satisfied, you can end up with MPJB metrics that are quite a bit lower than if you choose the different way to parameterize this conditioning. Okay, so that's the thing that mattered, number 1. The second thing that we noticed was when you integrate hand estimation into body estimation, it can actually improve the hand estimates themselves. The reason for this is if you just run a single frame hand estimator like Hammer, you actually end up with lots of things like monocular or scale ambiguities where the hands can be very big and far away or very small and up close. This is something we can visualize here where the Hammer estimates are in blue and then our model's outputs are here in purple. And so when you take these hand estimates and add the temporal context of our method, as well as just like the kinematic constraints of the possible joint angles of the arms, we can actually find that the hands estimated by our method, which has both the hands and body in the loop, are much lower than the original Hammer hands. And that's, of course, very useful, especially if you want to do things like capture interaction with the scene. So here I'm using this copy machine. Okay, last thing. One early concern I had with our project is that when you're doing the sampling process with guidance in the loop, it can run the risk of being very slow. And the reason for that is that each of these guidance steps is going to be an optimization problem that optimizes a ton of losses. So we have like hand losses, foot skating losses, and some smoothness losses. And if this optimization process is slow, right, sampling is going to be really slow just because you have to run this multiple times just to generate a single sample. And so we initially implemented this using just some standard PyTorch optimizers, so things like LBFGS or Atom. And we actually found that it was indeed kind of annoyingly slow. So just looking at the x-axis here, running one of these optimization problems, it could take between 2 and 3 minutes just to do a single step here. And now if we're running DDIM for sampling, you have to do that like 30 times just to generate a single sequence. It's just a little bit infuriating to run. So we spent like an obscene amount of time optimizing this. And we re-implemented all this optimization using Levenberg-Marquardt optimizer with basically like a lot of love and sparse Jacobians and things like this. And you can actually take this optimization time and squash it from 2-3 minutes to under 0.2 seconds.
2 minutes.
Okay, thank you. And one kind of fun note here is that I think is important is this is all implemented purely in Python with autodiff Jacobians. We don't have to manually write any Jacobians or any bespoke CUDA kernels or anything like that. So this infrastructure that's part of our code release is very general to other problems of this class. Okay, with that, that's basically the end. I just want to finish just with a sequence of results. So all of the results that have the Gaussian splats or sequences that we captured ourselves and then we reconstructed just to show that the humans are kind of correctly estimated in the context of the scene. And then we also have some results that have like point cloud scenes, and these are all from Ego4D. So here's me in the office. Okay, and then here I have a sequence of results. So this is from one of the COVID sequences in Ego4D. We have me using the coffee machine, frequent daily occurrence. This is me running around the office, less frequent daily occurrence. One of the piano sequences. And you can see kind of magically we get the sitting. I was kind of impressed by that. One of the kitchen sequences. And yeah, I think this is looping back. So if you're interested in more results, we have more results as well as the paper all on the website. So that's egoallo.github.io. And this is also like a big systems team effort that I definitely couldn't have done without everyone. So myself, Vicky, Maya, Yunxi, Leia, George, Yi, Andrew, Angju, big team. Appreciate everyone. Yeah, definitely couldn't have done it without everyone. So that's my last slide. Yeah, happy to take questions or anything.
Thank you very much, Brent. Anyone with questions? I have one. Did you try replacing, I love Hammer, by the way, but did you try replacing it with what Aria offers you, which is the hand, and like it gives you hand locations? And does that
Yeah, we actually have that result in the paper. It does improve with the hand estimates from Aria, but that only gives you like
the hand estimates from Aria. You mean even though it's just two joints?
Yeah, so for that, what we do is we take the local pose from Hammer, and then we take kind of the global wrist pose from Aria. And that's better than just using Hammer. I think it's mostly because Hammer is not super robust on the egocentric images. It's like one thing. And then also, I think the Aria estimation uses stereo, so it can just get the scale much better.
But I was wondering, if you only have the Aria estimates, does Hammer still improve?
If you only have the Aria
hand estimate, so you only have location of hand rather than hand pose.
I see. I think that's less likely. Yeah.
But you don't have that particular number.
No, I don't.
Okay. We've used EgoAllo. It's a very nice piece of code. Thanks for sharing. We noticed a little bit of extra hip movement. Is that something you've also noticed, or is it just our...
I haven't, but I think there are artifacts associated with the guidance optimization, and there's often things.
I was wondering if all the training on the dancing sequences Maria has provided resulted in extra hip motions in your sequences.
Yeah, so one thing is
that might happen.
We only train on a mass. because we don't have the simple parameters from EgoXO. That's kind of one of the motivations of Leia's project, I think, is we want the simple parameters. But as a result, I think the amassed sequences are super physical, where it's just like a lot of jumping and leaping and dancing. So we're very good at jumping and leaping and dancing. But it can struggle on like some of the more procedural EgoXO sequences. Like if you're doing a lot of stuff like the bike repair, it's quite challenging.
Any other questions? Thanks a lot, Brent. We move to the last talk by Kumar. We can see your slides.
Can you see the slides?
Yes, and we can hear you.
Okay, yeah. Let me start my timers. Yeah, hello. I'll be presenting expert AF, expert actionable feedback from video. Yeah, we propose a novel method to provide expert feedback on a learner demonstration. The learner demonstration can be any person demonstrating a physical scenario. Specific to Ego4D, it can be soccer, rock climbing, or basketball. And we want to provide a feedback that is aimed to correct the mistake in the learner video using either expert commentary. Expert commentary is where we have a written feedback, like the player is taking big steps to control the ball, but lacks body control. It can be expert demonstration of the video, a video of the person showing the corrected step, or an expert pose sequence. So we introduced this novel task of providing expert actionable feedback. We also create a weekly supervised expert feedback dataset for training and validation, which is based on Exo4D, and we manually verify the dataset for thorough testing. And finally, a novel multimodal method that uses video, 3D pose, and provides expert feedback. A brief look at the prior work. First line of work is skill learning from videos with datasets like How to 100 Million or Coin. And the work based on them is trained without mistakes because these datasets do not typically have mistakes, and thus they do not have any expert feedback. And these work do not focus on mistake identification and correction. Next, we have skill assessment and coaching on works like fitness, AQA, action quality. And they typically generate demonstration scores, which is not particularly useful when a person is trying to improve their skill. And some of the prior work requires activity-specific parameterization. No prior work uses video and 3D posts to provide expert actionable feedback. So now coming on to the dataset, Ego4D contains multi-view video and 3D poses and expert commentary. However, it does not contain paired incorrect and correct executions. So we use the dataset and recent LLM to create our training and testing set. So the dataset creation process is like this. So we use commentary with Llama 3 to generate the dataset. First, we take all the demonstrations and the accompanying expert commentary. So recall that this expert commentary is created when the expert is verbally explaining the video. So typically it's very verbose and not very good to train the model. So what we do is we summarize the expert commentary into a single sentence and also have a body part labeling, which maps the text to which body part is the feedback about. Like for example, in both these examples, the body part labeling is for legs. And obviously the expert feedback can praise the demonstration, or it can have some actionable feedback. So what we do is we collect all these labelings for a given particular chosen body part. And then we temporally align incorrect demonstration with the correct demonstration. For every incorrect demonstration, we choose which is the best matching correct execution and which is the closest. And that leads us to create the final training data, or where the tuple is an incorrect demonstration, a correct demonstration, and an expert commentary critiquing the learner demonstration. And then we filter the automatically collected data to create a clean testing set. Here are some examples of expert classification and body part tagging by Llama. So over here, the expert is talking about how the person is looking down during basketball dribbling, which is not a good idea. That might lose the sight of basket and her surroundings. And then we see that the incorrect part tagged is head. And this one sentence summary correctly captures the overall essence of the expert commentary. And we do this for all the expert commentary for the dataset. Yeah, and here are some examples of the final dataset. On the left, we see the person incorrectly using both hands to shoot a basketball. And on the right, the person is correctly using one hand for the force and just the other hand to guide, and also the angles are correct. And we have like several other examples. I'll pause for a few seconds so that you can read maybe one more example. Okay. And we do this for soccer, basketball, and rock climbing. These three are the physical scenarios in Ego4D. We also have dance, but dance is less deterministic, and thus we only focus on these three scenarios. So the training and evaluation tasks are expert commentary generation, where given learner demonstration, we have to generate the expert commentary. Expert demonstration retrieval, where given the learner demonstration, we have to retrieve the expert demonstration video. And finally, expert pose generation, where given the learner demonstration, we have to generate the correct pose sequence. We'll briefly cover the model overview. So the high-level idea is you want to convert all modalities to tokens and use the strong capabilities of a large language model. So the step one is to tokenize all the different modalities that we are considering. First, we have video tokenization, where we use intern video feature extractor and a visual mapper to convert the video frames into visual tokens. And we do the same with post tokenization, where we use PCT, which is a recent work on post tokenization. And finally, we have text tokenization, which is the standard text tokenization for any LLM. And then the step two is to use these tokens for the respective task. First, we have commentary generation, where we provide the learner tokens, the expert tokens, and then the task is to generate the expert commentary. At inference, we mask this out, so the only input is the learner demonstration. The learner demonstration. And we do the same, but with the order reversed for expert demonstration retrieval. And we have a similar structure for post generation. Okay, now coming on to some qualitative results. So this is for expert commentary generation. The ground truth says the climber is exhausted and struggling to make a move with poor hand and arm positioning. And our method is almost able to capture very similar issue with this video. On the other hand, on the right, we see PostScript, which is a method that converts pose into text, but this is more like describing the pose rather than providing any feedback. We have video chat to zero shot, which is not able to capture and provides very generic feedback, like they can improve by practicing their technique, warming up and stretching. If we fine tune Lava, it does improve the performance, but the performance is still lower than our method. Now we show examples of expert commentary, demonstration retrieval, and post generation. We see that the person is incorrectly having both hands extended when throwing the basketball, and the same is captured in the ground truth expert commentary and also our generated commentary. And the expert demonstration retrieval has the correct hand extension and shooting with one hand and guiding from the other. And a similar pose generation.
2 minutes.
Yeah. And we have a soccer example here where the body of the person is too straight when hitting the ball. And the expert commentary also captures, the generated expert commentary captures that the player's stance is too straight, which prevents them from generating the required power and control on the ball. And for the expert demonstration with retrieval, we see that the body is slightly tilted towards their left for a better shot and control. And we see a similar expert pose generation. So our method correctly identifies the mistake in the demonstration and provides actionable feedback. And last example we have is where the person is not jumping much and they're very straight without bending their knees much. And the same is captured in the expert commentary. And in the expert demonstration retrieval, we see a very good jump by the person here. Yeah, and then we see some failure cases. Over here, the left hand is incorrectly labeled as wrong. And the pose generation is also noisy, which shows that the expert actionable feedback is a challenging task. We briefly discussed the quantitative results. We experiment on both automatic matrix and human evaluation. For automatic matrix, we use standard language generation scores and standard retrieval matrix, and PA and PGP for pose generation. We compare against retrieval methods, visual language models, and pose and text generation methods. And our method outperforms all baselines and ablation by a significant margin. We see the same trend in human evaluation, where our expert feedback scores higher than baselines in human evaluation. In conclusion, we propose a novel task of providing expert feedback on learner demonstration. We introduce weekly supervised training and clean testing dataset, and our method achieves state-of-the-art performance on all three tasks: expert commentary generation, expert demonstration retrieval, and expert pose generation. Thank you.
Great work. Thank you very much. Do you think you need the expert pose generation? Wouldn't a human understand the pose from the demonstration retrieval? Or is this the case if you don't have a good enough demonstration retrieval, maybe?
Exactly. That it is, in some cases, we might not have the correct retrieval. So in that case, generation would be helpful.
I see. And the typical question is, if you've given this back to people, do you think they will be able to implement the required change to improve? Like, is the cycle closed, and what do we need to do to answer that question?
You mean pose generation alone, or?
No, now there is this person who is too straight in putting the ball,
Yeah.
right? You tell them they're
Yeah.
too straight. You show them the
Yeah.
person that is not as straight.
Yeah.
Do you think they will then know what to do to fix their pose? Is that sufficient info for the learner to proceed and improve, you think?
Yeah, to some extent, yes. We are assuming the case where we don't have, say, a coach that can explicitly like position you or hold you correctly. In absence of a coach, this is a good solution. Obviously, like coach is like an upper limit. Then that is the eventual goal of our system.
Mhm.
Yeah.
Any other questions to Kumar? Is the dataset, the labeled dataset of body part and rewritten text available, or is going to be available anytime soon?
Yeah, it will be available very soon. Yeah.
As in before Christmas, after Christmas?
Yeah. I think yeah. Like I can, I have it ready. Like if I
great.
can email, and yeah.
Fantastic. Looks interesting. I was thinking, reflecting on everything we've done with the pose, whether all the errors people have are in body poses that are not visible to them. Like, are we much better because we can see our body part and much worse because we can't see? Or is this not? I was just curious whether it has anything to do with visibility of the limb. But do you have any insight?
You mean from a first person perspective?
Yeah, exactly. Like if I see my leg, or if I'm looking at my leg, do I do better than if I'm not looking at it? Is visibility of a limb relevant to doing a task right? Maybe not. Humans are smart, but
Yeah. I think they can kind of guess, but maybe not the models. Like if you're using only egocentric videos, and this is, I think we also did an experiment. If you only use egocentric view,
Hmm.
it does not perform good. And in fact, exocentric is a better view for physical scenarios.
Any other questions or comments?
I think yeah, I wanted to comment on what you were saying, Dima, on the visibility and whether you need the visibility to be on most of these scenarios, at least the sports one that I know of. You're trained that the more you know, the least you need to see your body parts. So in dancing, you're not supposed to see where your feet are going because that's supposed to be like a novice thing. So it might be the other way around, actually. Well, from what I've seen.
Yeah. So indeed, even the pianists, right? They stop looking when they know what they're doing. I can act planning.
Yeah.
Thank you very much. Thanks a lot, Kumar. Thanks everyone who's spoken in the second session today, Friday evening. I'm starting to get tired. I guess everybody else is. But any final questions or comments? Okay, I will be pausing the recording for now, but in the meanwhile, maybe a bit